All right, good morning. So, good morning. So, we looked at the technique last time that you commonly called node voltage analysis and the other ones. But anyways, the key is that it's a very formal schematic technique that we can use to analyze any circuit. It's tedious, but it's formal. And I said several times, hey, you know, this looks like a computer program. And I also said that you could program this up on a computer. And so, not so too surprisingly, people actually did that. And there are many programs actually today available that allow you to do that. So, let me first talk a little bit about how circuit analysis, or especially circuit simulation, is useful. You may wonder, why do we spend so much time with paper and pencil doing it the hard way, analyzing circuits? Why don't we, if there are computer programs? So for that, let's go back and look at what we really are trying to accomplish here. Right? We are trying to design circuits, and so generally the way that happens is to start with some kind of a great new idea, right? Then, of course, you need to actually realize that. So first of all, you can't use a circuit simulator. You can't somehow tell the circuit simulator, this is my idea, now come up with the circuit. So there you kind of see you will need the circuit analysis skills and so on that we learn in this class. Then afterwards, finally, you come up with that circuit, and you know it's a complicated thing, has lots of resistors, voltage sources, and probably a few other components that we haven't talked about yet. And you go to the lab, and you've seen now how the lab looks like, right? You build the circuit with, imagine how many wires you're going to need there. You build it in the lab, you turn on the supply, and what happens?
It blows.
Maybe it blows up. Actually, sometimes it blows up, but most of the time, nothing happens. Nothing happens. How discouraging, right? Anyways, most of the time, if you put together a complicated circuit like this, it's like if you write a program with 10,000 lines, it doesn't do a thing, right? And certainly not what you wanted. So then you spend time in the laboratory, and well, I sort of arbitrarily said it's going to take 3 months, right, of very, very hard work, and ultimately find where the problem is, or probably there are about 10 or 20 problems, right? You find them one after the other, and several months later you have the solution. Now, if we design circuit like this, and remember, I mean, 37, that's not many components, right? Many components is 1 billion or something like that. If we design circuit like this, you still would be holding there wouldn't be any cordless phones, that's for sure, right? So there's got to be a better way, and So in practice, the better way is that instead of just running to the lab and putting together that circuit, we'll actually check it out first with the circuit simulator. Why is that a better way? Well, because with the circuit simulator, it's very easy to go and say, hey, I want to know the voltage at that node. I want to plot the signal at that thing. In the lab, you got to set up instruments, you get to the right place. There are lots of wires, it's messy, one wire falls out whenever you hook up the test instrument and so on. Right? If you do that, if you can do that on a computer, you can go much faster. So you catch 90% or 99% of all the bugs, and then in the lab, of course, you introduce one more because you hooked up the supply not quite right or something like that. But it's a little bit easier to find if you have only one error than 20 or so. Okay. So the first command, take that as you want, right? But we said that many times that node voltage analysis is a technique that really, you almost don't need to put your brain into action, right? You can just follow a schema and the right result comes back. If you don't make any mistakes following that schema, you can literally analyze any circuit that I give you. So in that sense, I guess the midterm is going to be trivially easy if you just don't make mistakes, right? Now, if you're like me, then you actually do make mistakes. So the midterm may not be altogether totally trivial. But computers, of course, they don't make mistakes. So for computers, node voltage analysis is just perfect. They just can do this for us. Okay? So, well, I mentioned already there are actually lots of programs that allow us to simulate circuits. The by far most famous one is called SPICE, and it was developed, you know where? Oh, Berkeley, right? By Professor Peterson. He is also the one who put the extra floor on Corey Hall. Largely thanks to his success with this program, lots of companies. Today there is not a single chip, not a chip in a cell phone, not a chip in a computer or anything. There's not a single chip that is being designed that hasn't gone through one or another version of this program SPICE before actually hitting the fab. So anyways, Don Peterson, he got a lot of goodwill from industry for putting that tool together and letting everybody use it, and among other things, that paid for our 5th floor in Corey Hall. Okay, so today there are lots of versions of this SPICE. You still can get the Berkeley SPICE, but most versions, either commercial or free, they have added additional features, for example, a nice user interface and so on. Here for EE40, if you know already one of these other versions of SPICE, by all means go and use it. If not, I recommend you use this tool here. One of the nice things, it's free. You can download it. It happens you have a PC. You can download it. You can run it at home on your own computer. Otherwise, you can use the instructional machines. So how about using this program? Well, that's how it looks like. And now let me try to do something dangerous. Let me try to actually show you how to use it. Oh, now, of course, see, that's dangerous. Now, convincing this graphics driver to actually show that program to me rather than my pretty kids. Okay, you know how to do that, right? You just stand on your head now and... there is... Maybe there is another way to do this. Well, but... But now my touch screen doesn't work over there. I think it is getting hopeless. Look, we're going to waste a lot of time if we do this. So sorry, it's not going to be a live demo. This graphics driver got ahead of us. Now at least, hopefully, it's still working. Sorry about that. I even trained using the program before coming to the lecture, but I didn't check out the graphics driver, so it got much fancier, so now it gets ahead of me. Okay, so, but if you start up the program, you will see this, okay? And then you see this, except for this stuff here, of course, is not present, right? So then you need to put all the components there. And for some components, you see there just at the upper right corner, there is actually a resistor. Well, you can click on that resistor and you can place it on your schematic diagram anywhere you like. Draw a normal schematic diagram. If you want to put the voltage source is a little bit trickier. So I'll try to explain it to you now. So there is another symbol that is further on that board. It looks like this. It looks actually like a digital gate. We'll see that symbol later. But if you click on it, you don't get a digital gate, but you get some kind of a pop-up window, and that has the names of a lot of elements that you could also add. And one of them is called voltage. That's the one you want. This one, it's called voltage. Okay? Then you get this element here also on the schematic diagram. Then you need to click on that other other tool. Then you can go and make all the wiring, right? So that it's all wired together. And you need to also assign a common node. SPICE does not work without common nodes because it uses node voltage analysis. And the first step you got to do is you have to choose a common node. And SPICE refuses to do that for you. You have to tell it where you want it. So you put that common node on the schematic, wire it all up. Then afterwards you have to choose an analysis. And that again is something where one of these commands, I think it's the little man that runs. You click on that little man that runs, and then it gives you it gives another pop-up window, and it tells you all the kinds of things it can do. Right now, what we're doing here in class is only DC operating point, the last one on that list of different analyses. There are other ones, like transient analysis as well. How do voltages change over time, right? Well, right now, we don't have any voltages that change with time. They're just constant. So we will get to the other analysis later. But right now, you just choose this DC operating point, say OK, and SPICE calls this .op, okay, from one of Don Peterson's students. That's still there, right? And you click OK, you run it, and then that's what you get. It tells you for every node, there is a node Vx, there is a node. So let me get to the schematic to what this really means. So there is a node, a common node. Well, that is 0, and SPICE doesn't bother telling you that the voltage here is 0. There is a node here Vx, and I found a way also clicking one of these buttons to call this one actually Vx. Okay. And the node at top there, I didn't give it a name. Then SPICE invents one. Okay? So now we have really three nodes, two nodes of interest, aside from the common node. So the one node is Vx, and it tells you what the voltage is there. And then there is this other node that I haven't given a name. And for these two nodes, it gives you the voltage. Okay? And then it also tells you what the current is through the resistors and through the voltage source. Kind of nice, right? So it does a little bit of extra work, just beyond node voltage analysis, give you those values. Okay? So incidentally, internally, SPICE does not use schematic diagrams. Internally, SPICE describes circuits in some other way using a netlist. You can see it actually lists resistor R1, resistor voltage source, the resistor R2. It tells how they are connected from Vx to ground, and so on and so forth, and gives the values. We are not using this description here in EE40. I just wanted to mention it to you that, hey, there are other ways to describe circuits, and you could imagine if you have a circuit that has, well, 1 billion components or so, maybe then a netlist or so is more convenient than a schematic diagram that is bigger than the United States, right? Okay, so that's just a side. Okay, so you can use this SPICE, and there is enough homework where we ask you to use it, and there will be a few labs where we also ask you to use it. We will not make terribly much use of SPICE in EE40 just because our circuits are relatively simple, and putting the stuff into SPICE or so is extra work that I want to save you. But feel free, right? The program is available for free. So feel free to use it if you like. And certainly, if you take other courses on circuit design, you will make very heavy use of SPICE. Okay, so then, what is SPICE good for? Well, there are things really that it's good for, and of course, it also has limitations. So first of all, it's really good for verification, right? This thing where you've designed a circuit, now you want to know, does it really work? Well, the circuits that my students design, and many other PhD students here in electrical engineering, they're very complicated, and we actually go and make integrated circuits out of it. Making an integrated circuit, designing it and so on takes 6 months to 2 years, so it's a lot of time. And afterwards, if you only find out that it's not working, that's not so great, right? You just wasted 2 years of your life. The other thing is, making such an integrated circuit can be very expensive, anywhere from a few $1,000s in the absolutely cheapest cases to more typically $20,000 to $30,000. And just the fabrication, right? And it can be as much as $10 million or so. Just one try, right? And so it's not like a computer program. You tried it and it crashes, and then you find the bug and recompile it, and a half hour later you're running again, right? There you just wasted $10 million perhaps, right? So we use circuit verification using computers to make sure that if there is any chance we can catch the bug beforehand, well, we really want to catch it. We were very motivated, yes?
Have any grad students actually made a $10 million chip or something? Has the university actually authorized that expenditure?
No, probably not. But our research expenditure in ECS, they run approximately $80–100 million a year, somewhere around there. So no, we don't do that. But we work with, if that gets that expensive, then we work with companies that they do an experiment and we somehow work with them on that experiment. So in that sense, yes, we are involved in projects that cost $10 million. Yeah. Also, we sometimes, when there are companies come up with new recipes to make smaller and faster chips all the time, and while they're still developing the process, then they often invite us to submit our own designs also, and they make them, and they don't charge us for us. Now, how much does it really cost? Well, on one hand, this is not production yet, and so they couldn't go out and charge money for the stuff. But on the other hand, they run the tools and so on, their whole research lab and their development engineers and so on. So effectively, they are paying millions of dollars to make our chips, right? So yes, but the worst thing is not the cost of the thing. The worst thing is that I just spent 2 years trying to get a PhD and I get a dead chip. Well, I really don't want that. Okay, so fortunately, right, in EE40 we have quizzes and you get 80 points, and well, that's not 2 years of your life, right? Okay, so it's much faster to do this circuit simulation, go into the lab, and you will agree with me, at least in a few weeks from now, when you work on more complicated labs. Debugging in the lab is possible. It's a very important skill, very good skill to have, but hey, it takes time, right? And that's also why you have to be organized and you have to do the pre-lab before you go to the lab, otherwise it takes forever. So then it's also good, when we do circuit analysis, for example, we say, you know, our wires are zero ohm resistance, right? Of course, that's not true. There is no superconducting wires in our circuits. So in practice, there is some wiring resistance. Well, if we were to include that and do our analysis with all this wiring resistance, it would be really terribly long. We would have suddenly 20 equations to write down for node voltage analysis. It would be terrible. But the computer, of course, can do this easily. So very often what we do is, if we suspect, for example, there is a wire and the voltage drop across that wire could be significant, when we do the simulation, we actually stick a resistor in to model that voltage drop. And then if we get a result that is different from what we expect, then we go and figure out whether it's that wire, right, or that wire resistance. Okay, so things like that. We will look shortly at other components where we will make idealizing assumptions when we do the analysis. Very important, because then we get a result quickly and we keep overview. But later we're going to use circuit simulation to verify that the actual component that is not quite ideal will also perform as we intend. So all of that said, right, SPICE is really great and it's extremely useful. We absolutely need it. I argued already today, nobody makes a chip without using one or the other version of this program. But it does have limitations. So already mentioned, right, a circuit simulator cannot tell you what circuit you should use in order to realize a certain function. You need to know that. And how do you know that? Well, we'll look at lots of circuits and we'll work with them in 4D, and over the years you collect more ideas on how to do things. with some exceptions, even if you figured out the circuit, SPICE can tell you what all the node voltages are and so on if you tell it what the component values are, but you got to find the component values first. SPICE doesn't usually do that for you. Okay? So the final thing that's very important, SPICE, of course, simulates. The simulator can know only what you tell it. So again, for example, wiring resistance, if you do not put wiring resistance into your model, into that schematic that you tell SPICE to simulate, then SPICE assumes happily that there is no wiring resistance. Or if you do not tell it, well, the component that I'm using there, the resistance could be a little higher or a little bit less than the actual value that I'm putting in there. Well, SPICE doesn't know about that and ignores and it simulates happily with whatever you stuck in. And consequently, even though you've checked the circuit with the simulator and in the simulator it works just fine, that does not always mean that it will work in practice. So sometimes you simulate, it worked fine in SPICE, you go to the lab, you build it everything right, all the wires in the right place, but because there's some differences between what you told the simulator your circuit is like and what your circuit really is, for example, the resistors are all a few percent smaller than the values that you put in the thing, because, you know, if you buy resistors, they're not going to be precisely dead on, right? Then it may not work in practice. So not all circuits that work in SPICE work in reality. But there are very, very few circuits that do not work in SPICE, but then in reality actually do work. I mean, there are special cases where that could happen, but it's very, very rare. So most of the time, in general, we are much better off figuring out. This is sort of, we have a necessary but not sufficient condition, to use a mathematical term. If we use SPICE to sort of pass the first check, but then we still have to build the stuff to make sure that it's actually working. And so in fact, I was editor for a journal on electronic circuits, and there when somebody sent in a new great circuit, and they verified it in SPICE, but they didn't actually build it, I told them, no way, we're not going to publish this. You go and build it first, because, you know, sometimes subtle things happen. Okay, so what skills should he get from this? Well, I've shown you more or less, right, how to use SPICE to verify the operating point, to verify the operating, find all the node voltages in your circuit. So there is a homework. There are some laboratories where you're going to do that. But again, we are not going to spend a whole lot of time running the circuit simulator in this course, and definitely you still need to be able to do circuit analysis, paper and pencil, and that's what we'll do mostly here. Okay? All right, so while I load, the next thing, are there any questions or so? Actually, the reason I asked this now, we sort of move a little bit, make a little bit of a break. Right? So far, we looked at resistors and voltage and current sources and how to analyze circuits with them, and we got something out, right? I even made some argument that, you know, you could get a career out of this just using resistors in strain sensors and so on. Maybe that's a little bit exaggerated, right? So, but anyways, to make it, we certainly can do many more things if we now add additional components. And one component we're going to add here is an amplifier. Okay, and there is a special kind of amplifier, it's called operational amplifier. So let's look at that, how that component is going to expand the kinds of things that we can do. Okay, so an amplifier, well, what does it do? It provides a thing called gain. Well, what is this concept of gain? Well, up here is again a strain gauge, right? And then it's somehow hooked up to a microcontroller. Well, let's look at this problem. In fact, is it this week, the strain gauge laboratory? Yeah. Okay, right. So you will notice that voltage Vx that comes out of the strain gauge is indeed representative of the strain that you apply to the gauge. But there is one problem, and that is that the voltage that comes out of the strain gauge is very small. It's millivolts, okay? And then, now in the laboratory, you have this big digital voltmeter that has many, many digits and a big amplifier inside and so on. And so for that instrument, it's not very hard to go and measure a few millivolts. Maybe the last few digits flicker and so on, but basically can do that. But it costs $1,000 and so on, right? And again, for the kitchen scale, that wouldn't be exactly the right solution. So more practically, if we want to put, as I said, we are going to do, if we want to put that voltage from the strain gauge into a microcontroller, that microcontroller expects a voltage that is, it depends a little bit on the version of the part, but roughly 1 volt, right? Full scale, meaning that the voltage varies somewhere between 0 and 1 volt, and then the microcontroller can resolve steps of maybe 1 millivolt, right? So it can see is it 0 volt or 1 millivolt or 2 millivolt, but 1.5 millivolt and 2 millivolts is the same thing. It can't distinguish that, right? And so if our signal is only a few millivolts, well, then it really sees almost nothing. Right? Maybe it sees whether a big weight is on there or nothing is on there, but that's about it. So how are we going to fix this? Well, we need to map these millivolts to this larger range of, let's say, 10 millivolts to 1 volt. Right? So we need some kind of a circuit that can take this voltage, the voltage Vx that comes out of the strain gauge, and multiply it with a factor, in this case, for example, 200, to map it to 10 millivolts to 1 volt, which then the microcontroller somehow can deal with. Okay? So that's what gain is, and that's what we're going to talk about, how we're going to do this. So just another example here. Imagine a radio, and this is again wonderful, right? In Google you find all sorts of funny images. So an antenna, right? If you were to measure what comes out of the antenna, now it would be more difficult, even for your $1,000 voltmeter in the laboratory. It would be difficult, but if you did it all right, you would find out that is it's almost random signal coming out. Of course, not completely random because there's radio signals hidden in it. Sort of microvolts are coming out of that thing, right? And so a lot of things have to happen before you can listen to this. Right? It has to go to a speaker, and one of the things that has to happen is you need to amplify this up to a much larger voltage. And of course, you need to also select just one channel of communication. Right? You wouldn't want to listen to 20 or 100 or 1,000 radio programs all at the same time. Okay, so gain is something that takes very small voltages and makes bigger voltages out of them, and sometimes takes small currents, make bigger currents or whatnot. Okay, so how are we going to do that? So here again, very schematically is shown an amplifier, right? We have a source. We have a source here that may be millivolts or even microvolts, and then we have a load, and here we want to have many volts. Here we have millivolts, right? And in between you have this thing that takes an input voltage, multiplies it by some appropriate number. I call that AV, and produces the output voltage. Okay, so we don't need this. All right, so how are we going to do that? Well, we try as you want. You can't do that with resistors. Perhaps with negative resistors, but then how are we going to make these negative resistors, right? So we need a new component to do this, and there are several choices, but the by far most important, the most common one is called operational amplifier. That's just the name. And so an operational amplifier is kind of a very simple beast, and it has some characteristics, and they're listed on this page here. So first of all, it's got a symbol. So you see that here, nice triangle. It has two inputs. They are labeled. Generally, one input is labeled with a plus sign, and the other input is labeled with a minus sign. And then it has an output that's at the tip of the triangle. So, and then it has characteristics. So, well, if it has inputs, there could be current flowing into the operation amplifier. Well, if the operation amplifier is good, in particular if it's ideal, then these currents that flow into it, into the inputs, they're going to be zero. Okay? In practice, of course, they're not going to be quite zero, but you know, a femtoamp, it's close, right? Very small. Would be very hard to measure actually the current that flows into a good op amp. Okay? Then the output voltage there, V out, is the operation amplifier computes from taking the difference between the two inputs that it calls plus and minus, right? And multiplying those with, say, gain AV. Okay? That's how it computes the output voltage. Totally mathematical thing, so maybe that's why it's called operational amplifier. And now comes the thing that is maybe most puzzling. What is the gain of this operational amplifier? Infinite. Okay? So when we go and buy an amplifier, buy one of these operational amplifiers, we get a thing that has infinite gain. Now again, in practice, it's not going to be infinite, but pretty darn close, like 1 million or so. Okay? So what is this? So the gain infinite. So first of all, who needs this? Who needs infinite gain? There's really no use for it, right? I mean, very large gain, maybe sometimes if we want to go from microvolts to volts, we need a gain of 1 million, right? But infinite gain, it's useless, right? Nobody needs this. So it's amazing that there are so many vendors of operational amplifiers and so many people that pay money for them. Is it possible to make a component that has infinite gain? Well, no. But close. Okay? So then let's try to get a little bit further on this puzzle. So if nobody needs it and it's not quite possible anyways, then why do we waste our time talking about this? So why? Well, operational amplifiers are made out of transistors, or you could also make one out of vacuum tubes, but forget about that one. Okay, they're made out of transistors. Now, transistors are complicated nonlinear elements and so on. We're going to talk a little bit about transistors, but not very much in depth. You're really going to talk much more about those if you take EE105 or EE130. So, but anyways, out of the sort of the conclusion from, if you go to these classes, you will find out that you can design amplifiers, but you cannot make amplifiers out of transistors that have a very precise constant gain. So, for example, if you were to try to build out of transistors an amplifier that has a gain of 10, then right, the output voltage should be simply 10 times the input voltage. That's what you want here. You may get an additional term. That's just how it works, because the transistors, sorry, they are not exactly perfect the way you want them. Then you would add another term that would be proportional to the voltage squared, right? And that, of course, adds distortion, and most applications, that's really not what you want. If you were to listen to this thing, then the music would sound terrible. It would sound distorted, right? And so this route of building amplifiers, it works, sort of, but it's not very good. So in practice, we're getting around this problem using a trick. And the trick is we take an amplifier that has infinite gain or near infinite gain, okay? And then we add that with one other principle, and that other principle is called feedback. And so the thing that actually, in the end, makes a gain, an amplifier with very precise gain, is the combination of something that has infinite gain and then something that has feedback or provides feedback that sets a very precise gain, for example, 10 or 200 or whatever. Okay? So this feedback thing is a very, very fundamental engineering tool or principle or so. It's used all over, and you probably will talk about feedback. If you haven't already, you will talk about feedback in many classes to come. Here we will sort of do only a little bit of feedback, just enough to build these circuits. But anyways, you will hear about more in other circuits classes. If you're interested in signal processing, wow, they use a lot of feedback. If you're interested in controls, and we have several courses on that, of course, also, then also use feedback in order, for example, to fly a heli automatically. Anybody try to fly one, they crash right away. But if you build a feedback controller, you can make them stable. If you want to control an entire refinery, so what are you going to use? Well, feedback. It's a very universal technique, very important. Okay, so we are going to use it here. So now let me give an example here. Let's suppose that we wanted to build an amplifier that has a precise gain of 20. So what we really, we look at this entire box here. This is the input voltage. This is the output voltage. And we want that V out is equal to AV times VI, and AV in this example is 20. Okay? That's what we want. Okay, so now we know what we have here. The circuit is given, but we know here that we have this operation amplifier. What is this little AV here? Yeah, and how much? What's the value? Infinite, right? This is infinite. We always, when we do analysis, we always assume that the components are perfect. Afterwards, we'll let the circuit simulator take care of the fact that they're not quite perfect and tell us if there is a problem because of that. Okay, and those two things, they are resistors, right? So let's try to analyze this circuit. So first of all, we can, of course, write an equation for the voltage Vf. That's the voltage here. Vf stands for feedback voltage. Notice this voltage goes from the output through that loop back to the input. So this is where the feedback is. What is Vf? Well, we can write that as a function of Vout. It's Vout times R2 over, thank you, R1 plus R2. So I told you, right, voltage dividers, they have to just jump into your head. Okay? So then we also know that Vout is equal to AV times V plus minus V minus, where V plus V plus is the voltage from here to ground, and the other one. So we actually can write that AV times V plus is VI, and V minus, well, that's just this voltage here, that's Vf. Okay? And then we can solve, and if we solve this, we get V out over Vi equals to R1 plus R2. So this is pure mass now, over R2 plus R1 plus R2 over AV. Okay, sorry, this ran a little bit over. Okay, fine. So that's what we got here. Now AV has what value? Infinite. So this term drops out, and now we have the gain of this thing. The gain of this thing is apparently equal to R1 plus R2 over R2. Okay, so, and this is the, note, there is a somewhat confusing but very convenient notation. There are two gains here. There is the gain of the operation amplifier, and it is infinite, right? And then there is the gain of this entire circuit that uses the operation amplifier. It is this capital AV, and it is set by the ratio of these resistors. So let's recapitulate. What happened here? Well, we used this component that has infinite gain, but then we applied feedback. And now the overall gain is set not by this component, which may be a little bit inaccurate, right? But it is set by just these two resistors. Okay? And these resistors can be made linear and so on. So the overall gain of the circuit, the gain that we want, is set by these resistors. And this we can set precise. This one here, all we can make maybe is big, but it's going to vary all over the place with temperature and whatnot, and has distortion. Okay, so that's the wonderful thing about feedback. If we have very high gain, then we can use feedback, and we can then set the gain by the network that is in this feedback loop, and in this case these are resistors which we can make precise. Okay? So, okay, so after this example, we'll go a little bit more into details and so on, how to analyze these circuits. Here we had to still work a little bit harder. We'll find easier ways to do that. But let's talk a little bit also about practical operation amplifiers. So practical operation amplifiers, I've said that already a few times. They're not ideal, but usually they're very close to ideal. They're good. For example, they have very high but finite gain. The only one limitations that every operation amplifier has is it's got a finite supply, and that one we really should consider, especially when we build something in the lab, right? If we hook up an operation amplifier to a 5-volt supply, don't expect to get 10 volts out of the operation amplifier. It doesn't have some miracle circuit inside to make a higher voltage. There are lots of other non-idealities in operation amplifiers. They can be very important in particular circuits that you might build. But, and you will find them in the data sheet, but we will ignore these for now, okay? So, yes, I mentioned the only non-idealities that really is important, especially in the laboratory, we'll consider, is the supply voltage, right? If the gain is infinite of the operational amplifier, then really, right, this is the gain, right? This extremely steep. Actually, the slope of this line here should be infinite, or the line should be vertical. I didn't draw it quite vertical because otherwise you can't see it anymore. Well, in practice, it goes up only up to the supply voltage of the operation amplifier like this. Okay? So that's the characteristic. That's the output voltage here versus the input, the difference of the input voltage. That's this difference here. Okay? If it was really infinite, then this would be just like this. Okay? But it will stop at the supply voltage. And so, so there are supply voltage, for example, this could be 5 volts here, and this one here may be minus 5 volts. Supply voltage that we have to hook up to every actual operation amplifier. If we go to the lab, you have to do that. We have to connect them to the supply, otherwise it's not going to work, right? Unlike a resistor that doesn't need a supply, well, an operation amplifier needs one to work. So now, drawing all these sources in your schematic, this VDD and VSS and so on for the operation amplifiers will really clutter your schematics. And once the schematics are cluttered and we try to analyze them, what happens? We get confused and we make mistakes. Okay? So in order to avoid that terrible fate, we simply, in most schematics, we simply leave these out. That doesn't mean that they don't need to be there, but because it's so absolutely obvious anyways that every operation amplifier needs to have a supply, we don't need to state it. We don't need to state that simple fact in every schematic, and therefore we can save some ink and some clutter by simply leaving those supplies away. And then maybe at the edge of the paper, write a note. When I build it in the lab, the supplies have to be plus minus 10 volts or whatever it happens to be the right value. Now there's one small little challenge, little trick if we do this, or a little thing to be aware of. Imagine that we wanted to apply KCL to an operation amplifier. Okay? Now, of course, we could sum up all the currents flowing in or out of the operation amplifier. Doesn't matter, right? I1, I2, I3, I4, I5. And the sum should be 0, right? Obviously. Now, the little thing is, if I didn't draw these, if I didn't draw the supplies, well then, I may forget that there is also a supply current I3 and there is a supply current I5. And of course, they need to be included in my KCL equation. Otherwise, the KCL equation is not true, right? So be very, very careful with op-amp circuits when you apply KCL around the entire op-amp. It's not going to be 2 if you do not include the supplies. Okay? Now, we're never going to actually do this when we analyze circuits with op-amp, so it's kind of a contrived problem. It will never happen if you apply the analysis techniques that we're going to learn here in EE40. But it has happened in the past in midterms, and because I don't like that people get puzzled and make strange mistakes and so on, I warn you of that now. Okay? Okay, so what about operation amplifiers? Again, they are, in practice, they're almost perfect, but also not quite. They're sufficiently from imperfect that there's probably 100 different ones or so that you can choose from lots of different vendors. They come with data sheets that are maybe 20 pages and application notes, so there is another 20 to 50 or 100 pages or so that tell you how to use them and what their characteristics are. So if you go a little bit further down in the data sheet, they will tell you, first of all, and you will need to know that in the laboratory, how to hook them up. So this port there, for example, has 8 pins, and inside are actually not just 1 or 2 operation amplifiers, and this tells you how to hook them up. This is the top view, so be very careful in the lab that you consider that's the top view, not the bottom view, right? That you, for example, correct the negative supply here and not inadvertently over there, because otherwise what happens? The port gets very hot and you may burn your fingers, okay? All right, so then in the data sheet, they also tell you always about maximum ratings. For example, you cannot expose it to 2,500 volts, but an ESD discharge of 2,500 volts that actually would not destroy the port. What else do we have? We have the maximum supply voltage of this port is 35 volts, and there are a bunch of other things. This can get pretty hot, right? When you solder it, can temporarily get 260 degrees Celsius. You can use it up to 150 degrees Celsius, but that is inside the operation amplifier. There, in the outside, usually has to be cooler, otherwise the heat doesn't get out. Okay, so then there are other tables in these data sheets. One number here in particular is interesting, and that's the gain. Okay, so so they call it something here. They call it large signal voltage gain. All right, fair enough. They tell you they measured it when they hooked up some kind of a load resistor. Then they tell you that they actually sell different parts, and they probably charge a different amount of money for the different ones, and they call the AI and the BI and so on. And what is the gain for these? Well, they specify the gain in volts per millivolt, M over millivolts. So that's just multiply by 1,000, right? What's 1 volt divided by 1 is 1,000, right? So apparently the typical operation amplifier will have a gain of 270,000, okay? But then they also say that the minimum gain is actually only 70,000, okay? And they even specify for the actual parts that they sell you, the minimum gain for this one is only 25,000. So be very, very careful when you look at the numbers in the data sheets when you design with operation amplifiers. Which number would you rely on when you design a circuit with operation amplifiers? This one here or this one there? What are you going to rely on? So yeah? The what? This one here, the lower one, right? You got to be very, very careful. Many operation amplifier, probably most, they will have a gain around here, maybe even a little bit higher. But you know, if then the temperature is low or whatnot, and your operation ampli has only this gain, it still should work. The thing that you built still should work, and you probably know electronic circuits that you have purchased or so on that work most of the time, but sometimes they don't work. It's frustrating, right? And so don't be a frustration designer, right? Make sure that you are a good, reliable designer, and so you have to design that it works still with the lower numbers in the data sheet. All right? I'll see you Friday.